Euclidean space. The Euclidean space is n-dimensional vector space. Okay, this is originally definition of that. The next we're going to start talking about so-called linear combination and affine combination. First is we call a linear combination. The linear combination, okay? So first we given a set of vector. A1, A2, all the way to AN belongs to n-dimensional Euclidean space. Okay, these are the very rudimentary definition of vector space. And then B can be represented as the following form. J equals to 1 to n lambda j times aj. Okay? Lambda j times aj. And lambda 1 to lambda n belongs to real number or dimension of 1. So they're real number. And this is mean it is a so-called linear combination. Okay? A real number. So B is a linear combination of vector A1 to AN. What does this mean in geometric space? If I have two, just have a 2 vector, A1 and A2, what is the linear combination for these two? Linear combination could be 2A1 plus 3A2, correct? Can it? Can it be half over A1 minus 3A2? Can it be? Still, they're a real number. Everybody kind of understand what I'm getting at? Can it be 1/2 of A2? Can it? Still, both are lambda 1, lambda 2, real number. So if I generalize this, lambda 1 and lambda 2 can be any number, real number. What does these two vector represent? Is that entire two-dimensional space, correct? Kind of makes sense now? Okay, next, we'll do another one, see if we can catch this one. Here, we call affine combination. Slightly different change. If I impose another additional constraint, meaning what? B equals to summation of j equals to 1 to n lambda 1 times lambda j times aj over here, but summation of j lambda j total equals to 1. Adding one more condition. What is this? Can you sort of help me out between these and that? So lambda has to add equal to 1. Is half, 1/2 and half is okay?
Yes.
Okay. How about 2 plus minus 1 A2. Is that okay? Yes? Add it to 1, correct? As long as. Could it be 2/3? How's that? This is not. What is it? Should be like that, correct? You kind of understand what I'm trying to say? So if these type of situation happen, it's geometrically what it is. Huh? It's no longer this. Smaller than this, correct? But it is what? A line passing through these. Make sense? And that's what we call a affine combination. Now, we're ready for another restriction. Third one we call the using different color so you kind of see. Why don't we use red color? We call it convex combination. What is this supposed to mean? It means similar to this, we're going to have B equals to summation j from 1 to n lambda j times aj summation of lambda j equals to 1. In addition to these two, I have third constraint, lambda 1 all the way to lambda n belongs to the R plus. Okay? What does that mean? The lambda can only take a 0 or positive value, no negative value. So this thing won't work. Does that make sense? No negative value, no negative value. Everybody okay? Can you tell me? In this case, which part of affine? So, affine combination is subset of what? Linear combination, correct? Convex combination is what? A subset of affine combination because it's more constrained. Can you tell me on this line which part is convex combination? The line segment in between these two vectors. Make sense? Kind of? And the last one. We call it cone combination. What is the cone combination specify? Similar. B equals to summation of j from 1 to n lambda j times aj total together. Okay? But I'm going to relax one constraint. Lambda 1, sum of lambda 1 equals to 0. The only restriction I'm going to have is lambda 1 all the way to lambda n belongs to the R plus. Okay. Now I relax some constraint. What happened here? Kind of getting a hint from here. What does that mean? Everything in this cone, right? Yes. Because this is this line segment, correct? Make sense? Yeah. So you see several papers specifically talking about linear, nonlinear programming optimization type of problem. A lot of time people using these full combination alternatively, we're going to use some of them later on. We're going to see these research papers, they're talking about these 4 different combinations. So you have 2 vector, okay? And then we're using these 2 vector, manipulate these 2 vector to create different combination and trying to perform so-called dimension reduction. You understand what I'm trying to say? Your solution space may be n-dimensional. Now I only want this 3-dimensional. And I keep rotating 3 different coordinates. And I'm using cone combination, using convex combination, using affine combination, trying to manipulate my solution space. Everybody okay with me? And later on we're going to see a so-called affine scaling, which is using the concept of an affine combination and trying to transfer the current solution space into a different scale. Make sense? So these are some fundamental stuff. Right now you don't see the correlation. But I'm telling you, in all the optimization methods, especially these kind of geometric search method, they are manipulating these 4 combinations. All right? Initially, your problem dimension may be high, and you just select a subspace of Euclidean space. And you're using these four different combinations or mixture them. and trying to reduce the solution space and trying to alternate them later on and trying to find the optimal solution. Does that make sense? A lot of things we call the dimension reduction technique. All right? All right. Let me talk about the other thing. We're talking about linear dependency and linear independency. We're giving a set S. It's defined as a set of vector in n-dimensional Euclidean space, A1 to AK. I only have K of them, all right? K could be N or K don't have to be N. S is linearly independent if, okay, if now N here is K equals to 0 if lambda 1 to lambda K equals to 0. The only possibility we make this happen is all the lambda equals to 0. Did that make sense at all? So if any one of them is not 0, this set of K vectors are not linearly independent. Because I can always, using that non-zero, move to the right-hand side. And becoming what? So for example, I have 3. Let me show you, okay? Lambda 1 times A1. Lambda 2 times A2. Lambda 3 times A3 equals to 0, for example. Everybody okay? If lambda 2 and 3 are equal to 0, however, this guy equals to -1. How's that? Everybody okay? This guy equals to x -1. What happened? What happened is I can move this term to the right-hand side. See this? Meaning lambda 2 times A1 plus lambda 3 times A2, A3 equals to what? 1 times A1. Is that correct? That means what? A1 is a linear combination of A2 and A3. So A1, A2, and A3 are not linearly independent. So A1 depends on A2 and A3 only. That make sense? Cool? So the only situation it could happen, we need this property later on to prove so-called span. We call the span of a vector space. Okay, we need that in a minute. So I'm trying to explain this in a special case. So the next we're talking about is S is linearly dependent if we can find one of these lambda not equal to 0 when we do this. Okay? So another one we're talking about is basis of En. Okay? It's defined as a set of linearly independent and we call the set S. S is a basis of En. Okay? And in other textbook, they refer as what? Equivalent to, say, S spans En. Which means the linear combination of A1 to AN represent the entire space of n-dimensional Euclidean space. So far makes sense at all? You're welcome to add additional explanation I have to the handout. So, question for me so far? So, for example, the special case of S, special case of that is correct? This is E1, E2 to En is what? E is a univector, correct? Univector. For the first position is 1, rest of them 0. Second position 1, rest of them. So there's definitely what? Linearly independent vector, correct? They represent each coordinates, correct? And S is spans. I'm going to prove a theorem, really easy. The reason we prove the theorem is just demonstrate some of the proving technique we're going to use later on. Okay, I'm going to start explaining. I'm just using this example, very simple to prove, and we're going to so here we have this is what I have. I'm going to rewrite it over here. Is that AN? Huh? A basis to n-dimensional Euclidean space, and let me repeat this again, see if you agree with me. If I say S has an n vector, okay, is a basis of En. What does that mean? Or S spin En. What does that mean? Every single point in En, okay, can be represented as linear combination of these. Understand what I'm trying to say? These vectors.
I have one question.
Sure.
We know that S ends equal to 1, and so what does this E1 is a unique vector?
Unit vector. Oh, En is equal to that. Ej equals to what? A vector. Everywhere is 0. There is only one place has 1.